Hi, class. Yeah, my name is Dr. Jim Rose. I am your instructor for this astronomy class, and we've had some issues with the different versions of Starry Night, and so the controls are not identical in both versions. I'm going to pause for just 1 minute, and I'll be back after I have started Starry Night, so I'm just going to pause. Hi, okay. What I'm going to talk about today is Activity 2 for your observation 2 out of Lesson 2. And the title of the activity is Rotational Motion of Earth. It's probably a good idea for you to go to Lesson 2, download the instructions for Activity 2 from Lesson 2, and then print them and follow along. I print these instructions first before I do my observations because it's much easier to do the observations rather than flipping back and forth between windows. So there are 5 parts to this observation. We have rotational motion in the northern hemisphere, rotational motion at the equator, rotational motion at the North Pole, rotational motion in the southern hemisphere, and then calculating rise and set angles. Clearly the common denominator here is rotational motion. So we'll be looking at the effects of the Earth's rotation on its axis to the night sky. And the night sky looks different depending upon your location on Earth. So what I'm going to do is I'm going to go ahead and start to read through the instructions. I'm going to go and share. And there's Starry Night there, so I'm going to choose it. And we are now sharing, so you should be seeing Starry Night in the display. Now, when you open it, there may be what's new. There may be a what's new window that pops up. The Cassini mission is ending, and in just a few days, and there's a little note about that that pops up. Now, when you first take a look at this, looks totally different than what we had for Starry Night College 6. You have a study guide on the left, and then you have a series of information relating to searches on the right. Now you can control this easily enough. In other words, you can get rid of it or hide them by a button that is on what is called the control panel or the control bar, which is this bar right here. That's this bar right in here. Okay. Now, if you haven't done so, take a look at the tutorial. That will give you a lot of information about how this system runs. And just by looking at that tutorial, you should be able to do the observations, even though the 2 versions are not identical. In Unit 1, we talk about the Earth, Moon, and Sun. Then the solar system, obviously, in this class you wouldn't look at it, but maybe you would take a look at Unit C, the planets. And then maybe star finding, the stars, galaxies in the universe would be something that throughout the course you could take a look at. We are stars and galaxies, and so you're looking at star finding, the stars and galaxies in the universe are probably the most relevant to what the class has. However, Unit A is helpful because it sort of introduces you to the use of the system itself. So what I'm going to do now, if you come over here, and these 3 icons control visibility of the sky guide. And on the right, we can toggle the search results. This will, if you do a search, it'll give you information, a lot of information about your search, and it shows up in the search panel. Okay, so you can get rid of that. So now we have the full view of our planetarium. So let's go ahead and take a look. Again, this is the control bar or control panel, and above that is the menu bar. So we have the home, we have a cursor icon, we have a drop-down menu that relates to the time and date. We have another drop-down menu that relates to the location of the observer. And if we come over here, we have a drop-down menu that determines the number of times above normal that the timer, the animation timer, will run at. Right now we're at real time. And then we have these three icons which control the sky guide, the graphing tool, and the search results. And we have a drop-down that gives us some other options, some sky guide, advanced find, telescope control, and so on. We might use those later. Field of view indicators. Basically, a lot of what's already here. Then you have the search text box right there. Okay, let's read it through. We are starting with Part 1, rotational motion in the Northern Hemisphere. Use the drop-down menu by the date and time field located on the control panel to select sunset. Click on the constellations button located on the button bar to show constellations. So the first thing is we want to show sunset. So we come over here, use the drop-down menu on the control panel or control bar, roll down to sunset and click it. Now the animation is still running, so I'm going to stop the timer by clicking the stop button there. Second thing, click on the constellations button located on the button bar to show constellations. Click the west viewing direction button on the button bar, or hit W on your keyboard to look towards the west. Okay, so the first thing is that they say click on the constellations button. You look at it, there's no constellation button. But if you go to View and scroll down to Constellations, we have several options. And the constellations, there are 88 regions of the sky which are known as constellations. In other words, astronomers have divided the sky up into 88 regions, and they call each of those regions a constellation. So those regions each have boundaries. And if you click on the boundaries, you can see that the boundaries of the constellations will show up. Now, many of us think that it's the patterns that we see in the sky which are the constellations, and indeed that in common usage is true. That would be these astronomical constellations, which are the stick patterns. Okay, so the precise definition of a constellation is one of the 88 regions in the sky. Now, if we click on labels, we're going to have each of those regions or each of those stick patterns labeled for us to find out what they're called. And if we go to Constellation and click Illustrations, the program will show you an illustration of the Greek god or character associated with the Greek or Roman god or character associated with the constellation. Gemini, for example, is the Gemini twins is one name of a constellation, and that comes from ancient mythology. So it doesn't tell you to do any of that. In addition, what we have is auto-identify. I am going to click the auto-identify because that sort of reminds us of what these stick patterns are. I'm going to unclick the boundaries. I am going to unclick labels, and I am going to unclick the illustrations. And we're just going to be seeing the stick figures for the constellations. Sometimes these are called asterisms, but I think your book calls them constellations too, so it uses a common usage. But you can see that the auto-identify is a feature that will give you the constellation that's immediately in your field of view or line of sight. And that's kind of nice. We'll be able to, we can kind of take a look at this. This is Serpens Cauda, and that's the name of this particular constellation. If you right-click on it and select it, and then if you can get on it just right, it is possible that let me change this to arrow. It is possible to have the program pronounce it for you.
Serpens Cauda, the snake's tail.
And this is Serpens Cauda, the snake's tail, is the name of that constellation. Okay, and so that's kind of a helpful device or feature of the program. So let's see. We're going to go ahead. I'll return it to the adaptive cursor. And now, read through. It says, click the west viewing direction button on the button bar or hit W on your keyboard to look toward the west. Well, there is no W. There's no button bar up there. We have a control panel and we've got the menu bar, right? So, again, if you look on view, it says face direction, and so we're going to face direction west. Okay, so you're going to face direction west, and if you hit the face direction west and then hit the space bar, it goes there immediately. If you just hit the face direction west and then don't hit the space bar, it takes a little bit of time for it to get there. Okay, so then it says select a time speed of 300 times or 300 times faster than regular time and keep this setting on throughout this activity. Watch the stars and constellations set. Do they set straight down, at an angle to the left, and an angle to the right? Okay, so we're going to come over here to this drop-down menu for our time set our time, and watch it. And you can see that the constellations are setting at an angle. They're coming down. They're setting at an angle to the horizon. Here's your horizon here. So that they're setting at an angle towards the right. Right? They're setting down towards the right. So you would then choose down toward the right. Now you repeat this process. You're going to go ahead and repeat this process for east, west, north, and south. When you come to the north, you're going to see that well, let's go ahead and go to north. I'll let you complete the lab yourself, basically. But let's take a look at what happens when you go to north. So I select north, and then I hit the space bar, and that gets me to the north quickly. All right, I'm just going to take a look, or for my own benefit, take a look at this one here.
Camilla pardalis, the giraffe.
That's Camilla pardalis, and it's the one for the giraffe. Okay, and so we're looking north. Now what we want to do, we're looking at the rotational motion. So we're going to go ahead and start this thing up again. We're at, I didn't tell you where we're at. We're at Union, Washington, which is up in Washington State. And so you can see that now it doesn't really set, right? Because when we look at the northern horizon, you've got constellations which are rising, and then on to the west, they're setting. So you can see that they appear to rotate around this point here. And it's important for us to take a look at the instructions, because it says here that and you can see that they're rotating counterclockwise, so you would select counterclockwise as your answer for that situation. Right now I'm on page 12 in the middle of the page. It says the Earth is a sphere rotating in space. The motions of stars and constellations you have been observing are caused by Earth's motion. The stars and constellations themselves are not moving to cause this apparent motion. The discrepancies in motion demonstrate by your different viewing angles are due to Earth's spherical shape and rotational motion. Our view toward the north clearly shows how the stars appear to move about a single point. That point being the projection of Earth's north pole out into space. We call this point the North Celestial Pole. The constellations revolving close to this point are referred to as circumpolar constellations. For higher latitudes, these constellations may never set. They simply go round and round the North Celestial Pole. Be sure to keep the equatorial coordinate system on as described previously. Okay, so we have to turn on the equatorial coordinate system. However, there are no buttons to do that. So again, you go to View, you drop down, and actually there is no equatorial coordinates for you to do. There are the two that we're going to be using most are the altitude and azimuth guides and the celestial guides. These are the ones that you're going to use. Now, the equatorial coordinate system is synonymous with the celestial guide. And what we want to do is we want to pick the grid. And that will display for us the coordinate system which is fixed to it's fixed out onto the celestial sphere, and as opposed to all the altitude and azimuth, which is fixed to the Earth. And so the celestial sphere is fixed and will rotate then. If we take a look, when we click on this, you see that you can very easily see that the celestial sphere is rotating, and that the coordinates, the celestial guides, are fixed to the sky itself. Now, I'm going to stop that. You can see it's rotating counterclockwise. Now, what it wants us to do, use your mouse to point to to point at the nearest star to the North Celestial Pole. Well, I don't see the North Celestial Pole, really, do I? I do see that it kind of comes over here, but it's certainly not. It's certainly not labeled. And so, what you're going to do is you're going to go back to View, come back to the Celestial Guide, and then click on the Celestial Pole, and that will label the North Celestial Pole for you. And then it says, determine the angular separation of this star from the North Celestial Pole. You can do this by hovering the mouse directly over the star. Watch the hand turn to an arrow. And then while clicking down, that is left clicking, and holding the mouse button drag the mouse over the north celestial pole. Your angular separation value will be given in degrees, minutes, and seconds of arc. It also says that by using the zoom control on the upper right that you're supposed to zoom in. And I don't know if I for some reason I skipped that line, but there is no zoom on the upper right. There is, however, a zoom down here on the lower left. And you can click the plus button, and by clicking the plus button, you can zoom in. Or you can, and that's probably the easiest thing for you to do, is just keep clicking that. Now you can use the hand to bring it back down, keep it in the center, and click some more so we get some good separation between the North Celestial Pole and the closest star, which is this is the star Polaris. Now we do have one here now. This is the one that we started with, and that's the one we're going to measure from. All right, so what you can do is you can use this hand. It says to put it over. Notice it changes to an arrow. Then you left-click and drag. It says 39:24. Now, there's a timer or something. It's very sensitive when you use that cursor. So if you use just the angular separation cursor, left-click and drag, for some reason it's more stable. .39, basically. Well, it didn't seem to be more stable today, but when I've used it before, it's been more stable. So 39 minutes. There's 60 minutes to a degree, so 39 minutes is about, what is that, 2/3 of a degree. And so you would write that down in the table on page 13. Write that down on the table of page 13. Okay, now what you want to do is you want to return to the previous field of view, and you can do that by going down here to the left and selecting 150 degrees field of view, which is your default, and that will bring you back to your original spot. Now notice that since I pulled the North Star, so it's in the center of my field of view, the horizon is now concave. And all you have to do is use your adaptive cursor, grab the edge, grab the horizon, and pull it back up. And now you have the normal view that you were before. So using your adaptive cursor, you roll it over the star, and now you can get the remaining information for that table. The star's name is Polaris. It's a double star or a binary, and it's 432 light years from Earth. So that basically wraps up my portion of this presentation relating to part 1. You'll read through here, you'll read the section which tells you that the North Pole is not the brightest star in the sky. It is, however, one that is unique in that it's fixed. All the other stars do seem to move around the North Celestial Pole, except Polaris. So it's a very good indicator of north, and that is why we use it for navigation. And let's go to part 2. Rotational motion at the equator. Let's investigate this further by traveling to other locations on Earth. First, let's travel to the equator. To travel to the equator, click the location button on the button bar, select the longitude tab, and enter 0 north for your latitude. You will then watch as you fly to your new location. Work through the same set of activities given in part 1 and complete the following guide. Okay, so essentially what you're going to do is, since there's no buttons, we have to find out how to get to the longitude tab. And that is here in this drop-down menu associated with your location. So you click that menu, then select View From, and it will open up a window that has a tab for latitude and longitude. You go to the latitude and you type in, and we're going to the equator, which is at 0 degrees north, and then what you do is you hit select, you view from this selected location. And you hit the space bar and you go there right away. Okay, so now we're looking north, and we're on or very near the equator. The first viewing location on the in that table on page 13 is west, so you can either push W and spacebar, or you can come here, go to face direction, west, and then hit the spacebar, and it'll get you there more quickly. All right. Now what we're doing is we're observing or studying the rotational motion that occurs. So you have to turn on the animator, and when you turn on the animator, what happens is that now you can see that the constellations are setting straight down onto the western horizon. And the reason for this is that from this point of view, what you're doing is you are looking at you're on a sphere which is now rolling through space from your perspective. When we were at the North Pole, or when we looked north, we saw that the thing was rotating. Actually, I'll hold that comment until we actually go to the North Pole in part 3. But right now, what it looks like is we're on the equator, the middle. If you think of it in terms of a basketball, now a basketball has the long stripes and it has the one stripe around the middle. Well, we're on the one stripe around the middle, and we have the ball so that the long stripes are horizontal, right? And now the ball is rolling along through space, and as it rolls along through space, it's rolling from west to east, and as it rolls along through space, the sky appears to, in this case, since we're looking west, appears to be moving downwards, and so that the objects are setting. Again, let's take a look at that. Now, we skipped the part in the instructions that mentioned the idea that what we can do is we can hide daylight. So if you go over to View, scroll down to Hide Daylight, you can turn off daylight, and that will not interfere with your observations. So you definitely can see that these constellations are moving straight down as we're on the equator. Here's the moon. So let's stop it. Now you will then have this situation where you look east, you look south, and you look north. And so just consider your perspective from where you are on the sphere. Okay, when you're at the North Pole, you're sitting on top of a spinning globe. Excuse me. Okay, let's go to part 3, which is on page 14. It says, let's next travel to Earth's North Pole. To travel to the North Pole, click the Viewing Location button, select the Lat-Long tab, and enter 90 north for your latitude. You will then watch as you fly to the North Pole. So, okay, again, we come to this drop-down menu for selecting a different location. We go View From. That opens up a window for the Latitude and Longitude tab. Okay, now what we can do is we can enter in. The North Pole is at 90 degrees north. And then we go View from this selected location, and it starts to roll there. I'm going to go ahead and speed that up by hitting the space bar. Again, you can watch it move by itself, but I prefer to speed things along a little bit. Okay, now we're at the North Pole. So now we're sitting on top of the basketball, and the long lines on the basketball are perpendicular to the floor, and so they're vertical now. And now, as we spin the globe, or as we spin the basketball we're sitting on, the basketball is spinning, so we're going round and round, and we don't, on Earth, we don't perceive our motion that way. So it looks like the sky is going round and round in front of us. And at the North Pole then, when you take a look at this, notice that these are all marked south. At the North Pole, every direction is south. However, you do have east, west, north, and south. If you point to west, for example, it'll pull you to west. If you point to east, you can see that it does, it's like turning around, okay? So it's like you were facing west, now you are facing east. But everything from the North Pole is south. And but you do have the situation that you do have you can look west, east, north, or south. Actually, west, east, north, or south is possible. Let's see what happens when you turn north and see what constellation is there. Basically, what it does is since you're standing at the North Pole, you have 360 degrees to go in a circle, to turn all the way around. So you go quarter turn from west would be south or north, and another quarter turn counterclockwise would be west. I'm sorry. Each quarter turn that you make will be in a different cardinal direction. That's what I'm trying to say. So appears that the moon right now is towards the north, and anywhere we go, it's going to be basically south. So you use the face direction thing here, and we go west, and we're going to do one more quarter turn, and that will give us the western view. And apparently, it's not the western view. It should be west, but that looks like it's an eastern view to me. Oh, it doesn't necessarily have to be, because it's 4 o'clock in the afternoon at the North Pole, and so it's not sunrise. Okay, so let's take a look and start the animation and see what happens. Okay, we're at the North Pole. We're sitting on top of the basketball. The basketball is turning, and as you can see, the sky, it looks as though the sky is turning instead of us. And the sun is not actually rising or setting. It's moving horizontally along the horizon, as are all of the constellations. Now, the Big Dipper here, so you know that's towards the North Star. Okay. And it goes from the left to the right. And you'll find out that any direction that you face, it's going to be the same situation. So you go ahead and work through the rest of those directions and make some comments there. Now, if we go to the southern hemisphere, let's see what it says. We are now at Part 4. It says the rotational motion in the southern hemisphere. How will Earth's rotation cause things to look different to us in the southern hemisphere? Use the location button to travel to any mid-latitude southern hemisphere city. Latitudes of 30 to 60 degrees work well. Okay, so what we'll do is come up here again to the drop-down menu on our control panel to set a different location. We go to View From. Click on that. The window opens up that allows us to enter latitude and longitude. Okay. Now what we can type in, let's type in between 30 and 60. That's 90. Let's type in 45, which is in between those two. And then we'll view a selected location. And we'll let the simulation run. I'll speed it up by hitting the spacebar. Okay, so now we are near some town in France, and the first viewing location is west. Again, we come up to view, look at the face direction, come down here to west, hit the spacebar, and now we are viewing west. And I am going to take a look at this again.
The Otis, the herdsman.
Now, I've always pronounced that as Butes, and it's called Baotes, and it's the herdsman. So that's the constellation that we're looking at right now. What we have here is we want to see what happens. We're in the southern hemisphere. Now we want to see what happens when the stars set in the west. Oh, now notice that I made a mistake. I have to go back to my location here and my latitude because I didn't change it from south to north. I didn't change the north to south. Okay, I needed to change the north to south, so it's 45 degrees south because we want to be in the southern hemisphere. And then I'm going to push spacebar to get there quickly. Okay, so now I'm in the southern hemisphere, and if I take a look and face west, that's the first direction in, hit spacebar to go there quickly. That's the first direction in the table that you have to fill out. So now we're in the southern hemisphere. And you can see we're in Cape Town, South Africa, as a matter of fact. You can see that now in the west, the stars set from right to left. They set down and to the left because we're in the southern hemisphere. And so the stars tend to set towards the, they rise and go across the northern sky and then set west from the northern sky. You can see they come out of the north here and set west. See, it says northwest right there, so they come out of the north, set west in the southern hemisphere. In the northern hemisphere is opposite to that. The stars rise in the east and they move across the southern sky, and then they set from the southern sky into the western horizon. But in the southern hemisphere, it's flipped. And so that's what you're noticing here. So you'll see that the stars are coming out, they're coming from the west, setting to the, from the north to the west, or down and to the left. Right, down and to the left. So that would be the way that you would indicate how those things are moving right now. And you're going to go through each of the other directions, cardinal directions, and perform the animation again and write down your data. Okay, so let's go to part 5, and part 5 is calculating rising and setting angles. We're only going to do the rising angle because they're both the same, and the values of them are both the same. It's just one's rising and setting. And there's a table here for us to work out. And let's go through the directions. I'll read them to you on page 15. Let's return to our home location. The simplest way to do this is to click the location button and select Return Home option at the lower left. But let's just click this on the control panel, the Home button, and it will return me to my home location. I'm going to turn off the animator. Everything has been reset, including the speed. Try and estimate the rising and setting angles you observed in part 1. You can do this by clicking both the Local Coordinate System button as well as the Equatorial coordinate system button, both located at the top right of the button bar. As you move time forward at 300 times, try and determine the angle of motion measured with respect to the horizontal as best you can. Determine the latitude and rising angle for your home location, the equator, and the North Pole, and complete the following table. The latitude column values can be found by clicking the location button on the button bar and then selecting the lat long tab. The rising angle column refers to the estimated rising angle as measured from the horizon. You may need to use a protractor if you have one. Hold it to the screen as the motion is turned on and while the local and equatorial coordinate systems are showing. The setting angle looking toward the west should be the same, but just a mirror image. Be sure to express the angle in degrees. Okay, so what we have to do is we have to go to View. We're going to enable the local coordinate system, which is the altitude azimuth. Okay, then we're also going to do the celestial coordinate system, which is, in this particular case, is called the equatorial. Select Grid. And that comes on. Now, I'm going to make life easier on myself. I'm going to hide daylight. I'm going to come over and I'm going to use the timer at 300. Okay. And you can do it with any star, but what I'm going to do is I am going to set this at sunrise, and I am going to face east to watch the sunrise. Okay. Now, if you click the animate button, you can see, and for the sun, there's a thing called a local path that you can turn on too. But you don't really need it because you can see that the sun stays fixed relative to the equatorial coordinate system, or the celestial guide here. And you can see that the celestial guide makes a nice angle with the horizon that you can measure. But if you didn't do that, you can also select a local path, and the system will draw a line for you. And the line shows you that the path of the sun is, very parallel to this line on the celestial guide. So you can either use that line and measure with a protractor, or you can use the celestial guide line here and measure with a protractor the angle between that particular coordinate line and or grid and the horizon, and that will give you your rise angle. And then to do the set, you can do the same. Now, if you don't have a protractor, there's an optional method on the bottom of page 15. And it says to get more accurate values for the rising angles, you can do the following. Select the angular separation tool by clicking the tool selection icon at the far left of the control panel. While looking toward the west, click down and hold on any spot on the local meridian line directly over the west direction. Hold and drag the cursor up along the meridian line. As you hold the button down, you will note that the two numbers are displayed. The first is the angular separation. The second is the direction as measured from the north celestial pole. The red lines of the equatorial coordinate system all lead to the north celestial pole. Thus, this procedure, if done properly, can yield an accurate rising angle, the second number. Okay, so that means let's go to west. Again, all you really have to do is type W and then the space bar. Now we're looking west. Now in this situation, it says go for the angular separation angular separation cursor, and we'll left click and lift it up, and you can see, well, we want to be parallel to those lines there. So it was 42.8 degrees. 42.8 degrees. It was the second number. Now, I don't know if you was able to see that very well, but when you're doing it yourself, you left-click, lift it, and it's the second number, not the first one. The first one gives you the angle of separation. The second one gives you the position from the North Celestial Pole to it's called the position angle, and that's the angle from the North Celestial Pole. And that angle from the North Celestial Pole then is actually equal to the rise angle, or the set angle in this case. And it was, what did I say? It was 42.8, I believe, or we'll call it 43. But my latitude, so you come up here to find out what your latitude is, write that down. My latitude was 47.2, and so the 42.8 would work. But if we just used degrees, it was 47, and then the set angle that I measured was 43. If you add those two together, 47 and 43, you get 90. And that's the key. You add the latitude and the rise angle, you're always going to come up with 90. Now, to make that a little bit more clear, if we go to the equator, again, go to the equator, go through that same sequence. Equator is at 0 degrees. And so view from there. Hit spacebar to speed things up. Okay, now look west. I'm just going to push the W button and the spacebar, and that will get me to looking west. We're looking at the set angle here. If we want, let's look at the rise angle. So we'll go east. And let's back it up to the sunrise. And you can see that the local path is already written there for you. You can see it's straight up, right? Now, if we hit the animation timer, notice that the sun rises straight up. So the angle between the sunrise and the horizon is 90 degrees at the equator. Again, this is because you're sitting on a sphere that's rolling through space. So it appears that the sun rises straight up. Now, the latitude at the equator is 0. The rise angle is 90. 0 plus 90 is 90. It still works out. So when you do your, when you fill in that table, you'll have 0, 90, and then 90 for the sum. Now, if we go to the North Pole, so we're going to go to the, change our location here. View from the North Pole again was at 90 degrees north. So go 90 degrees north, and I'm going to speed it up by hitting the space bar. Okay, so now, and here let's move it to, well, there is no sunrise, but let's look east. And so we're looking east. Let's change our time. Let's move it back Now here, let me set it. Let's say 7 a.m. There we go. Okay, so let me take off that local path item here. And we'll back it up a little bit more. Well, actually, we don't need to because it's not going to rise. But now we're at the North Pole, and at the North Pole, we're going to go ahead and start the simulation. You can see that the sun is, doesn't rise. It's parallel to the horizon. That means that there's no angle between the sun's path and the horizon, and the angle of the rise angle is 0. 0. So what we have a situation is that the latitude is at 90, the rise angle is 0, so when you add the two together, it gives you 90. And I'm going to return now to the whiteboard, and we will discuss a little bit why that is. So let me here close this up and return to the whiteboard, close sharing. So we've stopped sharing, and I'm going to return here to the whiteboard. Hopefully you can see it now. Okay, so the situation is this. This circle represents Earth. The circle represents Earth here, okay? And this line here represents the line of sight of somebody who's standing at the North Pole and is looking straight up at the North Celestial Pole. NCP is the North Celestial Pole. So you're standing at the North Pole, and you look straight up, and you see Polaris up there, and right next to Polaris, just a half a degree away, is the North Celestial Pole. So you're looking at the North Celestial Pole. That line of sight follows, if you follow it all the way down, it follows and it intersects the equator, which is not, it should be parallel, but it's not. So it intersects the equator here, okay? And if you're here and you look straight up, the zenith is the point that, from any point where you're on the Earth, if you look straight up, that point is called the zenith of the observer. So the line the line of sight which connects the zenith of a person here at the equator intersects the line of sight with the person here at the North Pole. And those two make a 90-degree angle. Those two lines of sight make a 90-degree angle. Now the angle between the observer's line of sight and the line of sight to the North Celestial Pole is the rise angle. It turns out that is the rise angle. And in this case, the angle is between 2 is 0 degrees, right? The angle between at the equator, the angle that my line of sight makes to the zenith and the angle that the line of sight of somebody at the North Pole would have to the North Celestial Pole, they lie in the same line, so that the angle between those two lines is 0, so that the rise angle is 0. But down here on the equator, the zenith of the observer at the equator is perpendicular to the one of an observer at the North Pole. That is the line of sight to the zenith. On the equator, the North Pole is at the horizon. So if I'm here, if I'm there, then if I want to look towards the north, I have to look out here towards the horizon. Okay, so if you'll remember, when we were at the equator and we looked north, you'll remember that the North Pole was lying on the horizon. And at any rate, that the angle between these two lines of sight is 90 degrees, and that corresponds to the rise and set angles at the equator. Okay, so if we go to a situation where now the person is here at the okay, we have a person here and looks less than 40 degrees, but the latitude, which remember, if you if we come here, right, this is the latitude line. You know, latitudes are like ladders; they're horizontal, right? That's like the crossbars in the ladder, so they're horizontal. And this angle, the way the angle is measured, it's measured from 0 degrees at the equator. So the angle that we're talking about here, is this angle. This angle right here. This is the angle. Oops, it's not doing it. This is the angle that we're talking about here. That's the 40 degrees of latitude right there. Okay. So when a person is here, their zenith is right here, and their line of sight then makes if you extend it to where it intersects to the equator, makes an angle of 40 degrees with the equator, and that's their latitude. Well, remember that the rise angle is the angle between their line of sight to the zenith and the north celestial pole, right? Well, from here to here, right, from here to here, that's 90 degrees. So what's left here is 50 degrees, and then that is the rise or set angle is 50 degrees, which is what's left here. And that's the angle between the line of sight to the zenith of one observer as compared to line of sight to the North Pole, to the North Celestial Pole of somebody who is at the North Pole. That gives you your rise angle. So, kind of, if it didn't make any sense, just think of it that the rise angle at the equator is 90 degrees. The rise angle at the North Pole is 0 degrees. So in between that, the rise angle goes from 90 down to 0. And the latitude tells you how far down it has gone from the equator. So at the equator it goes at 90, and then you come up here, the latitude is 40 degrees, so you subtract 40 from 90, that'll give you your rise angle. And that's how it works. I hope that makes sense, and I don't think there's anything else that I have to talk about. So I'm just going to, my big struggle, this is like the 3rd time I've done this, and my big struggle is making sure that this thing is recorded and I have access to it so that I can give access to you guys. I will, once I figure this out, I will post a link and you can watch it.